Collision detection is a major challenge in simulating deformable models. It can take up to 90% of simulation time. One of the major challenges lies in self-collision detection. In this scene, we see the skirt collide with itself. We decompose the problem into checking for possible interference among adjacent primitives as shown on the left and non-adjacent primitives in the mesh as shown on the right. We compute a chromatic decomposition of a mesh. To illustrate the concept, we show a simple example. As shown here, we make sure that every neighboring polygon of the polygon highlighted in red has a different color. Next, we make sure that every polygon at distance of 2 in the mesh also has a different color. Here we show the chromatic decomposition of a triangulated mesh. In this split-screen video, we highlight the benefits of 2.5D overlap tests. On the left, we show the PCS in orange obtained using an AABB hierarchy. On the right, we highlight the PCS in orange after performing 2.5D overlap tests. We have implemented our algorithm and tested it on a high-end PC with a 3.4 GHz Pentium 4 processor and an NV6800 graphics card. In this example, each step takes about 100 to 150 milliseconds to perform collision detection for the opening curtains. We have also integrated our collision detection algorithm with a surgical planning method for inserting a catheter into the liver arteries for delivering medication directly to a tumor. The catheter is a deformable, tube-like object as seen in this video segment. As the deforming tube is inserted into the arteries of the liver, it must be checked for self-collisions and with the nearby blood vessels. The catheter is constantly in a near-contact, parallel proximity situation throughout the entire simulation. Our algorithm checks for all collisions at roughly 12 to 18 frames per second, outperforming previous algorithms by at least 1 order of magnitude. In this example, our algorithm checks for collisions in 400 to 500 milliseconds per time step. Our algorithm is able to achieve at least 1 order of magnitude performance improvement over prior methods. Here, we demonstrate our algorithm on an animation of a folding, layered skirt. There are many wrinkles and folds, causing the skirt to self-collide at many different locations. Our algorithm checks for collisions in 300 to 500 milliseconds per time step.